Oh, this. I'm gonna find this. Is it this one? Yes.
Really?
Literally, all you need is highlights.
It is. Yeah. It's all depending on. Dude, like we're back in the States for like and no, but I get into
What do I have? Sorry.
yeah,
Okay. So, we were talking about voltaic cells. Yeah? Okay, alright. Good stuff. We're talking about voltaic cells, and remember, if you're ever given a voltaic cell, you can basically answer any question you want as long as you can find out the half reactions, right? If you can find out the half reactions for a cell, you can pretty much determine anything that's going on inside that cell. So as long as you can find the half reactions, that's going to be a really good thing for you. Keep in mind, these are all the things that they could ask you about, but they're probably not going to, right? They're going to ask you maybe 2 of these things, and then they're going to move on. They're going to move on and test you about different stuff. We want to talk about a different type of cell. First of all, is this a voltaic cell or is this an electrolytic cell? This is electrolytic for sure, 100%. There's a couple reasons why, but what's the quickest way for you to be able to identify? It's in 1 cup, and also there's a power supply, so that means it's electrolytic. Now, it says predict the voltage of the following cell and identify if the reaction is spontaneous or non-spontaneous. It's not going to have, it's not going to ask you which one is the cathode and which one is the anode unless it gives you a positive and negative terminal of the battery. The first thing I want to ask you, where do electrons come out of on a battery, the positive or the negative end? Negative. The negative end. So that means electrons are heading this way. So is this electrode going to be the cathode or the anode?
Cathode.
Yeah.
All right.
So the cathode is where the electrons head to, right? Because that's the site of reduction. So this would be the cathode, right? As long as you understand that, then we're good to go. That means that has to be the anode, whatever. Okay, so what we're going to do is we're going to predict the voltage of the following cell and identify if the reaction is spontaneous or non-spontaneous. If we want to predict if it's spontaneous or non-spontaneous, we need the half reactions. In order to get the half reactions, what do we have to figure out first? Strongest oxidizing and strongest reducing agent. Max.
Since there's something on this diagram that kind of tells, is that also a viable reason to like say up or down?
Okay, well what do you think?
Like since there's a power supply.
Yeah, that's exactly right. As soon as you see a power supply, boom, electrolytic cell. It has to be electrolytic because you don't need a power supply for a voltaic cell, right?
Mm-hmm.
So what's our strongest oxidizing and what's our strongest reducing agent? Do you guys see carbon on the list of redox, like reduction half reactions? No. Is it ever going to be there? No. Why?
It's an inert electrode.
It's an inert electrode. It's not reactive. I know, but that's the reason why you're not going to see it. Inert means not reactive. So we're not going to see it. Okay, what's the strongest? Let's list our major entities. What are all of our major entities here? We got carbon solid, but we know that's not going to react, so let's not even put it.
Potassium hydroxide.
Okay, so we got potassium, and what kind of potassium is it?
Ion.
Potassium ions, and they're liquid. And what else do we have? We have hydroxide ions.
Water.
There's no aqueous.
We don't have water. Okay? So that's actually really important for us to identify. Because it's not aqueous. This is like if we took potassium hydroxide and heated it up so much that it liquefied the ionic compound, this ionic crystal structure. If we gave these ions so much energy that the positive and negative ions separated from each other, and they became a big soup of positive and negative ions. That's all that's happening here. There is no water. So okay. Do you have a strongest oxidizing agent in this list?
Okay.
That's our strongest oxidizing agent. It's how strong of an oxidizing agent is it?
Second last one.
Other than lithium, right? Okay, and then so what has to be our strong? What not what has to be? Okay, not what has to be. Okay, because potassium could conceivably also be our strongest reducing agent, but is hydroxide our strongest reducing agent? Yeah, it is. Strongest reducing agent. So let's identify, okay, at the cathode, potassium plus is going to receive an electron. It's going to turn into potassium solid. And then at the anode, hydroxide. What the hell is hydroxide going to do?
It's O2 gas.
Okay,
2H2O plus 4 electrons.
good, thank you. 4OH turns into O2 gas plus 2 H2Os, liquid, and it gives off 4 electrons. So this is happening at the cathode, and this is happening at the anode. So figure out the cell potential for this cell, please. Max question.
Since there's no water there, would we not write aqueous in the half reactive?
Oh God, you're so right. That's just the force of habit, isn't it? Liquid, liquid, and then we're gonna make water. But probably that water is just gonna evaporate out. Okay, so the reduction potential of this is negative 2.93, right? And we're going to subtract the reduction potential of that, which is positive 0.40. So we're going to take our negative 2.93 and we're going to subtract 0.4, and we should get a voltage.
Oh, yeah.
Right?
Yes.
Yeah.
I do.
So it's really important that you understand that we're always going cathode minus anode, right? It's not bigger voltage minus smaller voltage. It's just whatever's happening at the cathode minus whatever's happening at the anode. And of course, is this spontaneous or non-spontaneous? It's non-spontaneous. Give me 2 reasons why you think this is non-spontaneous. It's got a negative voltage. It's uphill. It requires a power supply. Yeah. Good, Kate. Cathodic protection, real quick. There's 2 ways to protect a cathode or protect a metallic material from oxidizing. The first and honestly the primary way, the cheapest way, not cheapest way, but kind of the easiest way is to cover it in something inert. So let's say you've got some iron. We've got these iron atoms. I'm drawing FEs just for those of you at home who can't see, okay? So these are FEs. And there are some things, right? There are some things that we want to protect this iron against. Most notably oxygen in the air and water from the rain, right? So this water and oxygen, they're attacking the iron constantly. Yep. So all we have to do is put a layer Mr. Zakowski is doing something. I think. Nope, somebody just made a mess and they're literally vacuuming it. So, alright, that's fun. Okay. Okay, so what we want to do is we want to put something super non-reactive. What's another way for saying non-reactive?
Inert.
Inert. Good. Oh my god.
Yell at him. I know you're angry. Go Hulk.
So what things are inert? If you wanted to protect this reducing agent, what would you cover it with?
Diamonds.
Gold.
Would you cover it? If you wanted to protect it with something non-reactive,
Platinum.
okay, but if you wanted to protect it with something non-reactive, do you want a stronger reducing agent or a weaker reducing agent? Well, wait. If you want, no, stronger reducing agent or weaker. If you want to cover it in something that's not reactive, you want a weaker reducing agent.
Cover it in aqueous chlorine.
Okay.
Yes, always cover it with chlorine. Always cover it with
So let's cover it. Let's cover it in a layer of gold, right? Because gold's super unreactive. But what happens? What happens if we accidentally get a little scratch in here?
Then you got problems.
Then we have problems, right? That's exactly right. What am I doing? I'm doing this. Because if we... There we go. Perfect. Good.
Yeah.
Fantastic. So if we accidentally scratch it, can the water and oxygen come into contact with the iron now?
Yes.
And they can oxidize the iron, and that's bad for whatever you want. For your bridge, or your car, or your whatever, your pipeline or something like that, that's not a good thing. So that's one way of doing it. We can cover it in something inert. Or, the totally different thing, we can go the totally opposite way. We can attach a sacrificial anode to it. Now the thing about a sacrificial anode is let's say we've got a big chunk of iron. It's a pipeline or a bridge or something that we want to predict. All of a sudden I have a South African accent. Good. So you got a big chunk of iron and it's buried in the ground. And in the ground, it will oxidize. There's water and there's oxygen and it will totally rust. So what can we do? Well, we can take this thing, we can cover it with something more reactive than itself. A more reactive reducing agent. And we don't actually have to cover it. We can literally just attach a wire and we can have a stronger reducing agent. Why? Why could we attach it to a stronger reducing agent? Okay, I'm hearing some pretty good things. What's going to happen the moment this iron oxidizes? What's it going to turn into?
Rust.
Yeah. Okay, but
But
what is iron Fe solid going to turn into?
Iron oxide.
Yeah. So but most importantly, iron 2 plus. Are we okay with that? Just specifically, it's going to turn into iron 2 plus. So the moment it turns into iron 2 plus can steal the electrons from this strong reducing agent, right? So all we have to do is put magnesium or aluminum or zinc. Lithium's probably not a good thing because it'll immediately react with water. You don't want to actually want something more reactive than water. But anyways, any of these things. Could you use copper?
It's in the, what's that?
That was a choice on the question.
Yeah.
It's the,
I don't remember why.
what's the girl with the torch?
The girl with the torch?
Statue of Liberty.
Oh, yeah. Yeah, the Statue of Liberty. Yeah.
You know the girl, the name with the torch?
Yes, yeah, the girl with the torch, otherwise known as the Statue of Liberty. Yeah, totally. So what? She's covered in copper, right? Yeah, so she's covered in copper, and copper oxidizes in water and oxygen, right? So it can oxidize and turn that bluish-green color. But could copper spontaneously react with iron 2 plus ions? No.
It's a stronger reducer.
It's not a stronger reducing agent than iron, though. Than iron? That maybe then, yeah. Right? So we want, as soon as iron, where the hell's iron? As soon as iron turns into iron 2 plus, we need something that can turn the iron 2 plus back into iron. So we need a reducing agent that's stronger than iron. So zinc, chromium, aluminum, magnesium, all sorts of stuff. Okay? So there's lots of things that we could add that to, but anyways. Okay, hopefully that makes sense. So we slowly sacrifice this anode. It gets eaten away and gets eaten away and gets eaten away. Eventually you have to protect it, but you're sacrificing that so that this is strong. Okay, pretty much the last thing. The chloride anomaly. We can draw this cell if we wanted to, right? It's going to be carbon, solid, carbon, solid. In here is going to be sodium and chloride ions. Oh, thank you. I'm so used to using sodium. It's going to be potassium ions, aqueous. Chloride ions, aqueous. That's a terrible cube. And water. Okay, when you look at your list, what's a stronger reducing agent, chloride or water?
The list, it's water.
It's on the list, it's water, right? But because of something called the overvoltage, it has to do with the activation energy required for water to be able to react here. It's not actually water. Under most normal circumstances, it actually ends up being chloride. So our strongest oxidizing agent is water. That ends up being our strongest oxidizing agent, but this ends up being our strongest reducing agent. And you have to be able to see that. You have to be able to spot that from a mile away on the diploma exam. It's been on the diploma 4 semesters in a row, so it'll probably be on it again.
What about 2 miles?
What? That I don't care about.
Me driving up to third.
Yeah.
I get a feeling.
Okay, we're not going to do this. If you want, this is in your notes. This is literally straight out of your notes. So we're going to skip this because we want to move on to something else. Okay? Half cell stoichiometry, if we're given a half reaction, or if we can figure out a half reaction, we can use unit analysis to predict the current, the amount of time, or the mass required for a cell while it's in operation. So for example, chromium can be plated from a solution of chromium 2 ions. How much time is required in minutes? Required to plate 25.7 grams of chromium onto a steel bumper using a current of 30 amps. So what's happening is we've got a bumper, we've got a chunk of metal, right? And we want to plate onto here chromium solid. But it's not going to plate as chromium solid, it's chromium 2+ first. So is there a half reaction here that we can see?
Chromium 2 plus aqueous plus 2 electrons turns into chromium solid.
Chromium 2+ is gaining 2 electrons and turning into chromium solid. So what we want to know is we want to know how much time will be required for this. But this is a lot like any stoichiometry problem. What do we always do? How do we build a stoichiometry problem?
You start with what you want.
You start with what we want, but before we're going to do that, we're going to put all of our information below any of these pieces of information. How much chromium do we want? So we want 25.7 grams of this stuff, okay? Immediately, I don't know about you, but immediately, because it has something to do with mass, what else do you need? Molar mass. Because stoichiometry is all about moles. So what's the molar mass of chromium?
52 grams per mole.
52.00 grams per 1 mole. Okay? And then what other piece of information did they give us?
The amps per mole.
Think back. Don't say anything out loud. Think back, but don't say anything. Don't say anything out loud. Okay? Think to yourself. Amps. That's interesting. There's something that should be clicking in our mind when we think about amps. Don't say anything out loud. Do we like amps? No.
I love them.
Instead of amps, what do we want to write? Coulombs per second. This is how much charge every second is being transferred to the bumper through this half reaction. So, now that we know that there's 30 coulombs every 1 second, all you need, can you get time out of this somehow?
Yeah.
You can get time out of this. All you need is the coulombs. Well, how do coulombs relate to anything else? Faraday constant. Good. 9.65 times 10 to the 4 coulombs per 1 mole of electrons. Do you kind of remember this? A little bit? Now that we have all our pieces of information, now we can go ahead and we can do our unit analysis. I don't know about you, but I like to figure things out in seconds first and then turn them into minutes. But it's up to you. The time in seconds. So if you want time in seconds, how are you going to get time in seconds? You got to put seconds where? On top or bottom? On top. So 1 second for every 30 coulombs. So you just got to cancel out coulombs. That's literally all you have to do. How do you cancel out coulombs? Faraday's constant, 9.65 times 10 to the 4 coulombs per 1 mole of electrons. Okay. Okay, you've canceled out coulombs, right? Cancel.
Is it 9.65?
It is 9.65, sorry. It's Tuesday, the 83rd day of our semester, and probably nobody's brain is working right now, but that's fine. Okay, coulombs canceled. We just have to cancel out moles of electrons. How do you cancel out moles of electrons?
Molar ratio.
2 moles of electrons.
The molar ratio between your unknown and your given. 2 moles of electrons for every 1 mole of chromium. So moles of electrons cancel. Now what do I got to do?
You gotta be like, hey guys.
Yeah, you got to be like, hey guys.
Molar mass.
Where's my calculator?
Where is your calculator?
I'm wondering the same thing.
Look at this. How beautiful is unit analysis?
Too much.
Coulombs, coulombs, moles of electrons, moles of electrons, moles of chromium, grams, grams, love it.
Oh, that's not.
It says moles of electrons, yeah. And remember, all of that stuff is in the data booklet.
I feel the buttons, but I can't.
Right here. Right? Coulombs per divided by moles of electrons. $3,180 or something like that. Yeah. So you're gonna get 3,180. What, like something seconds. Okay, in seconds. That's in seconds. Do we want seconds?
No.
No. So how do we turn seconds into minutes?
Divide by 60.
Yeah, you can use unit analysis. You can just divide by 60, right? So you should get 53.0 minutes. So it's going to take 53 minutes to plate this bumper with enough chromium to cover it. At least in this particular scenario that I made up with no experience in a bumper plating operation. Yeah. Yeah. Do you have a question, Max?
No, I was just going to say something.
Okay.
I'm learning something.
Yeah. Oh, you wouldn't know. Ah, okay. I mean, not that I think you need to right now, but that's never a bad thing. Doing okay, Jonas? Yeah, you're good. All right. Okay. This is the last thing we're going to review, and I don't even know if we're going to get all the way through it. Do you want this at all? No.
Wait, promise we watch a Bill Nye.
You did?
Yeah, I did. I thought. I was like,
Oh, by the way, another big one.
Yeah, good. Well, Kelton, sometimes people lie,
That's something you gotta
but
learn.
they lie to protect you from the truth.
And that is for writing.
No.
what's the honest? I was excited for the Bill Nye video.
You know, Bill Actually, yes,
Nope. Probably not. Yeah.
Mr. Walton, I hyped myself up for that Bill Nye video.
I know. I apologize. Yeah.
We're coming back.
Sure. Oh, Shohei! Boo! The only reason why I'm making fun of you is because you made a big stink about it too. You actually did. Anyways, whatever. Okay, so we're gonna do our energy review now. It's okay if we don't get it all done. That's totally fine. It's the way it is. Energy can be found in two forms: potential energy and kinetic energy. Now, potential energy is energy stored in chemical bonds.
Someone's having a shower.
Yeah, somebody's vacuuming up there. Yeah.
They're still vacuuming?
Yeah.
That vacuum must suck.
So, for example, a carbon-hydrogen bond is high energy, whereas a carbon-oxygen double bond is super-duper low energy. Now, you don't have to know that, but you have to know that there's a difference. So when we rearrange, when we take a hydrocarbon, say propane, and we burn it, what are one of the products you make when you burn propane?
CO2.
Carbon dioxide, right?
Whoa.
Carbon dioxide has CO double bonds. And so what's happening is we're taking an incredibly high energy bond, we're rearranging the atoms, and we're turning it into a low energy bond. What happens when you go from high to low energy?
You lose energy.
Our system here loses energy. Does that make sense? Now, where is that energy going to go? Energy can't just be destroyed. It can't just disappear. It goes to its surroundings. Good. So the kinetic energy is the energy of motion. And so a particle of water moving slowly versus a particle of water moving really fast, is there a difference between these two energies? Yes. Yeah, which situation has more energy?
The fast moving one.
Yeah, the fast moving one, right? So this is what I mean. If we're talking about rearranging atoms, if we're talking about a chemical reaction, that's talking about potential energy. But if we're talking about water heating up, changes in temperature, that's a change in kinetic energy. Hopefully that makes sense. The two are related, but hopefully that makes sense. Energy is constantly being converted between those two forms in a chemical reaction. We can calculate the amount of energy released by capturing the energy with a calorimeter. This process is called calorimetry. During a calorimetry experiment, a student burns 3.7 grams of methanol, and the energy is transferred to a calorimeter containing 400 milliliters of water. Draw a picture of the scenario. Okay, let's draw a picture. What's going to hold the water? Some sort of a container. Yeah, probably not styrofoam, because there's a flame underneath, but that's fine.
That'd be fun. Science experiment. Let's see what happens.
It's made of styrofoam.
Okay, so
Wait. You realize it's our last chemistry class of the year?
now I'm curious. So the flame, the methanol is turning in, it's chemically reacting with the oxygen in the air, and it's releasing the heat, and the heat is being absorbed by the water. But what's the problem with this particular situation that I just drew?
It's open.
This is an open system, isn't it? And what do we want? We don't want a closed system.
Oh, an isolated.
We want an isolated system. Because a closed system is that's where matter can't leave, right? Like materials, molecules can't enter or leave. But energy can still escape, or energy can still enter, and we don't want that, right? What we want is we want an isolated system. Now that's different from a closed system, right? Closed systems are in equilibria. We don't want isolated systems in equilibria because we want to be able to heat it up and cool it down. Here, we want all of the energy to remain inside the calorimeter. Because this is an isolated system now, all of the energy that's lost by the candle, where is it being forced into? The water. It's being forced into the water. So the energy, that's not how you spell energy. So
It's okay,
I
Walter.
keep wanting to put an L in energy. The energy lost by the methanol equals the energy gained by the water. So as long as we can figure out the energy lost or gained, doesn't matter, whichever one, then we can figure out the energy lost or gained by the other thing, right? Because if I pay for a car and you know that the dealer gained $20,000, can you guess how much money I lost in that transaction? 20,000. It's the exact same thing. The energy gained is the energy lost, right? So let's draw a change in potential energy and a change in kinetic energies of the system. So the first one is potential energy. What's happening during the combustion of methanol?
Energy is being released.
Energy is being released, right? Our products and our reactants. And what's happening to the kinetic energy of the water?
Going up.
Yeah, it's gonna rise, and then at some point in time it's gonna flatten out when the reaction's done, right? So from this graph we can get kinetic energy, and we can relate it back to the potential energy of our system. So what we want to do, without doing much review at all, we want to figure out if the temperature of the water increased by 50 degrees Celsius, we want to calculate the molar enthalpy of combustion for methanol. Where do you want to start? Does anybody have any ideas?
Water.
Oh,
4.1.
use it constant.
Can we use change
Isn't it the neat formula?
Yeah, you could do Q equals MC delta T,
Yeah.
right? Yeah, that's fine. We didn't do that. We didn't do Q equals MC delta T, right? What? Well, we can't do products minus reactants because we're not being given a reaction right now. But there's a bigger kind of point going on here. Let's read. Don't read this. Read tips and tricks number 1. Read tips and tricks number 1.
Specific heat capacity of water.
If you're heating up, at the moment you see water's changing temperature, what you should immediately look at the specific heat capacity of water. What is the specific heat capacity of water? 4.19 what? So either joules per gram degree Celsius, and that's gram of water, right? Grams of water, or 4.19 kilojoules per kilogram of water degrees Celsius. No, I said kilogram of water degrees Celsius. Gram of water degrees Celsius.
Oh.
Now, we know we're going to have to use unit analysis, okay? The reason why we're going to have to use unit analysis is because we're heating up water and we're going to have to use a specific heat capacity. The question I want to ask you, what are you looking for? The molar enthalpy of combustion, okay? So what is molar enthalpy measured?
Kilojoules over moles.
We're looking for the molar enthalpy of combustion, and it's measured in kilojoules per mole. Now, I want to be very clear. It's kilojoules per mole of what? Kilojoules per mole of what substance? For methanol, right? Per mole of CH3OH. I'm getting closer?
I think they're gonna.
I know. I don't know what the hell is going on.
Did they like dump like big?
No, but I think they might be going from one station to another, vacuuming something out. I don't know why they do, but whatever, doesn't matter. Yeah. Yeah, go ahead, yeah. Okay. Hey, where are you going to be able to find kilojoules anywhere in here?
The images. Yeah, that.
Specific heat capacity, right?
Yeah.
4.19 kilojoules per kilogram of water degrees Celsius. Okay, we are halfway there. We found half of our units. We just need to cancel out everything else and put moles of methanol on the bottom. So what do you want to cancel out? Let's cancel out degrees and heat at the same time if we want, or sorry, degrees and mass. So 50 degrees Celsius, that was our change. And what else? Do you know how much water was here?
No.
It says
400
earlier.
milliliters.
400 milliliters.
Oh, I didn't know we had that.
400 milliliters is 400 grams.
Just one.
So 0.4 kilograms. Kilograms of water. So our degrees and our kilograms of water and our kilograms of water cancel out. So we've got our kilojoules. That's great. We know how much energy was released. But we don't want energy released, we want molar enthalpy. So what do you have to do now? Yeah, you got to use molar mass and you got to cancel out grams. Good. So we could use molar mass. So it's 35.05 grams per 1 mole of CH3OH, just because. And then we're going to cancel it out with 3.7 grams?
Yeah.
3.7 grams. Grams, you get moles. Good. So just go ahead, do that on your calculator and try and figure out what it is. I apologize, I started to run out of room because I really went kind of pretty hard on the beginning on that one. But yeah.
What's that?
What unit is the 35.05? Is that grams?
That's grams per 1 mole, yeah,
Alright.
of methanol. Yeah, it's going to be 793 something
What's the unit closest to you right now? The one?
grams.
No, I mean, like, what is it? Like, where did you get it from?
I got it from the mass of methanol that we burned
Oh, okay.
up here, 3.70 grams.
Okay.
I apologize, it's a little bit disjointed, but. Would you get, Jonas, 793? So 793.835 kilojoules per mole. But what, I mean, is that the answer?
No.
What do we have to round it to?
7.9 times 10.
Yeah, 7.9. We actually need 2 digits, right? 7.9 times 10 to the 2 kilojoules per mole. And one final question. Is the molar enthalpy of combustion positive or negative?
Negative.
I don't know.
It's
It's
negative.
because if it drops, the energy is releasing, so it's a negative.
What did you draw here? A negative enthalpy, right? So our molar enthalpy is negative. Would you agree the methanol is releasing energy when it burns? Yes. So it's releasing energy when it burns. Is that... Ooh, man, we went through a lot of stuff.
Yes.
Are we okay with that?
Yes. Last time we go into more stuff.
No, not break time. You're in Chem 30. Yeah. Yeah, you gotta go.
Can you just scroll up to 1 second?
Yeah. So on the next slide, it's talking about the specific heat capacity of a bunch of different things. What I want you to do is I want you to look for the specific heat capacity. What did I put? Of copper and aluminum?
Yes.
Okay, so find them on your data booklet and write them down. And figure out which one is going to go to a higher temperature if we add the same amount of energy. Yeah.
Copper and aluminum. It's going to be copper.
What's copper's specific heat capacity?
0.385.
0.385. So the C of copper, 0.385 joules per gram degree Celsius. And what's the of aluminum?
0.897.
897 joules per gram degree Celsius. Okay, so if you had the same amount of energy, let's say you had 10 joules, where could you buy more degrees Celsius? With the copper or with the aluminum?
Copper.
With the copper. right? So the lower the specific heat capacity, the more it's affected by changes in temperature, right? The specific heat capacity is also a good indication of the ability to store kinetic energy. Basically, it's just saying it's how much does it cost, right? If something costs more, then you're investing more money in it. Does that make sense? So if something has a higher specific heat capacity, you have to invest more energy to change its temperature, so that it's storing more energy. So which substance will require more energy to increase its temperature by 10 degrees Celsius, water or tin? I don't know, let's see. Let's just work it out. What's the specific heat capacity for water again? 4.19 joules per gram degree Celsius. And then what's the specific heat capacity for tin?
0.227.
0.227 joules per gram degree Celsius. So which one do we have to sink more money into in order to raise it by 10 degrees? Water. You need to buy, water's more expensive, right? So it stores more energy when it changes temperature. That's just, whatever, it's fine. We're not going to be asked about that, but just interesting. Okay. Tips and tricks for answering enthalpy questions. There's 5 tips and tricks here, and we're going to be able to go through maybe 2 or 3 of them. If you're heating up water, then you probably have to use the specific heat capacity. So there's a question that's almost exactly the same as what we just did, but it's just using a different substance. So it says, what is the molar enthalpy of combustion? What? That doesn't make any sense.
What? The molar?
The molar enthalpy of combustion is for propane. Holy man. For propane. It's not embarrassing because this is like every day in my life, but that's fine. The molar enthalpy of combustion for propane is negative 2,043 kilojoules per mole. What mass of propane will be required to change the temperature of 300 milliliters of water by 20 degrees Celsius? So basically, all you have to do is what mass, right? We would look for mass. And then mass you can get from, what do you think? There's molar mass, then you'd have to cancel out moles with the moles here.
Ratio.
Then you have to cancel out the kilojoules with the kilojoules of water, and then blah, 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 blah. Okay, you can do that. I will put up a key on Google Classroom later on today or later tomorrow about this. There's a second tip. Anytime you're given an equation with an enthalpy associated with it, you can use the information as like a molar ratio comparing the moles of a substance and the energy. So, how much energy will be released from the following reaction if 2.75 grams of formic acid are combusted? So what I want to know, how much energy, where are you going to get energy out of this reaction? That's here, right? Yep. So this much energy. Now, this much energy is being released when how much formic acid is reacted? 2 moles, right? You can use this information and this information, and they form like a little bit of a molar ratio. This becomes 508.6 kilojoules for every 2 moles of formic acid. Does that kind of make sense?
Yes.
I really do not want to skip past this until everybody kind of really truly understands this, because this is maybe the most powerful thing that I think a lot of us didn't understand when we did the energy unit, is that this creates its own ratio, and then we can use this information when we're doing unit analysis. Max?
If the energy change is negative, can you still do it?
Yeah, is this energy change positive or negative? This energy change is negative. Because it's in the products, right? That means it's releasing, or it's a negative energy change. So just because it's positive here doesn't mean anything. If it was positive as a product, and if it was positive as a reactant, those are 2 opposite things, right? So what do we want to do? Where are we going to get? What do you want from this? You want energy, right? So you want to know how much energy in kilojoules is going to be released. Where could you possibly get kilojoules from in this reaction?
The 548.6.
Yeah.
And if you divide that by 2.
508.6 kilojoules are released for every how many formic acid? So 2 moles of formic acid. Okay. So all we have to do is cancel out 2 moles. That's it. 2 moles of formic acid. What could you possibly get moles? Yeah, because we know something about grams, right? Grams and moles, that sounds like it's molar mass. So what is the molar mass of this substance? 12 and 32 is 44, 42, 4203. Sorry.
46.
Yeah, 46.
That's better.
12 and 32 is 44, plus 2 is 46. Okay. So 46.03 grams, nope, per 1 mole. That doesn't work, does it?
Flip it.
Flip it. 1 mole of formic acid is, what do we say, 46.03 grams of formic acid?
Yes.
0.022.
It's 0.03. Because hydrogen, and carbon all have a 0.01 at the end. When you add it up, trust me, it's going to be fine. And then we're going to 2.75 grams of the formic acid. Grams, moles, boom, done. No problem. Like, is that fairly straightforward?
Yeah.
That's tough, though. That's really tough. Getting this equivalency, understanding that there's this relationship, is super powerful, and I want to make sure that we all kind of understand that. Cool. I'm assuming somebody's calculating this, right?
Yeah,
15.1928. 1928 kilojoules. So 15.2 kilojoules. Perfect. And it would be negative, but it doesn't really matter. It doesn't really matter. They're not going to test you on that, so whatever.
Isn't numerical diploma all multiple choice?
Yeah, and numeric response. How many questions do you have on your diploma?
40,
60. There's 44 multiple choice and 16 numeric response. 16, 1-6, yeah. Yeah, there's not 60 numeric response. What? You're going to have a sheet of paper in your booklet that you rip off. At one side, no. It's going to have a couple columns for your multiple choice, and then it's going to have a few columns for your numeric response. And then on the back is going to be all your personal information. Like you're going to have a little sticky thing that you have to put on there, a barcode. So.
How long does it take for the results to come in?
I don't know. I've got no idea. I think something like 3 or 4 weeks, but I honestly have no clue. Well, because there's like 80,000 people in Alberta writing the chemistry diploma exam. Yeah, I know, but how long do you think it's going to take to run 80,000 of this test, and then 80,000 of the other tests, and then of the physics and the biology?
That's not my problem.
That's not your That's not your problem, Matt.
Will this so fun? Because it's a diploma exam, will we add it to our power school, or do we need my pass?
No, you need MyPass to get your diploma results, right?
Yeah.
Yeah, you guys all have MyPass?
Oh, yeah, I think so.
Okay, well,
You better go get it.
talk to your connections teacher. Don't talk to me about it, because I don't want to have to deal with that. Talk to your connections teacher. Yeah.
Wait 2 weeks.
Okay. If you're given multiple equations, if you're given multiple reactions, probably you're using Hess's law. Do you remember how to use Hess's law? No.
Sort of, not really.
No? No?
Yes. It's
Yes?
They give you
Can we just make a bill video?
Thanks.
Or
Yeah.
there's also formation.
I like that one idea.
I like the information that
They weren't even on yet.
Man, I'm so glad they're vacuuming out there. They're cleaning up all the stuff that the teachers have to clean up in the next 3 days. So that's amazing.
Can we go help?
No.
Okay.
Do you seriously want to go scrub down hot plates
It's
No.
probably better
with
than
wax and
Hess's Law.
well, it's better than Hess's Law?
It's probably way better than Hess's Law.
Just because you said that, I'm going to force you to do this now. Let's do this. If you're given multiple equations, then you're probably going to have to use Hess's Law. Calculate the energy change. Now, we want to make this chemical reaction out of these chemical reactions. Do you remember what you're looking for? Macy. That's fantastic. You want to look for one substance in the first equation that you can only, or one substance in the main equation that you can only find in one of these, right? And then adjust it by multiplying or dividing, and also, multiplying by negatives, that kind of thing. So what, CH4, let's look for CH4. Can you find it in only one equation? Yes. Where can you find it? Equation number 2. So is it good the way it is? No. It's on the wrong side. So what do you got to do to the enthalpy? Multiply by -1. Okay. That will, remember, what happens when you flip the enthalpy?
Flip the equation.
You flip the reaction, right? Okay, what about the next thing? NH3. Where are we going to find that?
One.
The top one. So what do we have to do?
Same thing.
You have to multiply
-2.
by not -2, because then the 2 becomes a 4, right?
Oh, sorry.
-1/2. So you can multiply by -1 and then just divide by 2 if you wanted to. It's whatever. Yeah, 0.5. That's fine. Yeah, totally. Okay, what else in here do you need to look for? HCN.
What if I divided the top equation by
2.
That's cool?
By -2? That's fine. Yep.
Yeah, okay.
Yep. HCN you find in the last equation, so what do you got to do? You got to divide that by 2, right? You don't have to flip it at all, you just got to divide it by 2. Have we used all 3 equations?
Yes.
Yes, then we can be pretty certain that we don't have to do anything. We don't have to force ourselves to do the math here, to do the chemistry and add up all these equations. We can just do this. So do that times -1/2, do that times -1, and that divided by 2. So that's going to be... Is it going to be positive, like 15 or positive 40?
Which one?
No, the whole thing.
Oh,
When you just add up everything. Oh no, that's going to be positive. I'm way off. Yeah. So Preston, what'd you get?
Positive
255.65 kilojoules. Love it. Perfect. Was that okay? If you get a Hess's Law question, are you going to be happy or sad about that?
Happy.
Okay, nice. Matthew.
When you make that 255.7.
No.
It is. No.
Oh yes, you would. 255.7.
It is addition at the end.
Yeah, but what you're doing, when you divide this by 2, you need 3 significant digits.
Okay.
When you multiply, you know what I mean? So it's just whatever, it's fine.
And the dividend
It'll be multiple choice, right? Or it'll say give me your 3-digit number, in which case you would have to round this to 3 digits or whatever, right? So it'll be okay. Okay, let's keep motoring. We got this, we got this, we got this. If you aren't given any information about a question, if you're given no information at all, except maybe just the chemical reaction, then do you remember what you have to do about that?
Not products minus products.
Yeah, it's not products minus products.
No, it says products.
I know. I noticed that earlier, but I was hoping nobody would say anything.
You literally taught us this yesterday.
I know. Okay, what is the molar enthalpy of combustion for butane? Okay, I'm asking a question. Am I giving you any information?
Not really.
No. So what you have to do is you have to develop your own chemical reaction. What would be the chemical reaction for the complete combustion of butane? C4H10 plus a certain amount of O2 gives you CO2s and H2Os. Now, because we're combusting it, what's going to be the state of matter of water? It's going to be a gas. It's going to be a vapor, right? There's lots of ways you can do this, but I just want to make sure that we're all on the same page. Okay, well, there's some things we can do, right? Okay, 4 carbons, 10 hydrogens, so what do I got to put here? 5. So I got 4 times 2 is 8 oxygens, plus 5, so that's 13 oxygens, right? So what could I put here? So you could put 6.5, or you could put 13 over 2, or you could double everything. You could double everything, and the 6.5 turns into 13, right? So that's fine. So now, if we want to calculate the enthalpy of this reaction, the enthalpy of this reaction is going to be the sum of the enthalpy of the products minus the enthalpy of the reactants. So put huge ass brackets, okay? Massive brackets.
Massive.
4.
We don't need to monetize for that.
I think I'm pretty sure.
You had an ad on it the other day.
Did I?
Yeah.
Does it just automatically put up ads? Because I don't have.
I didn't see the ad. I just saw it in the feed. Like there was a yellow bar. Like,
Do you use an ad blocker?
not on my phone.
Oh, that's interesting. Because I use an ad blocker on
You
everything.
need,
What?
yeah, I think it's once you get like 100, maybe it's 1,000. That's when you can start.
1,000 views?
Subscribers.
Well, I don't have 1,000
I
subscribers.
think that's when you can apply for monetization.
Oh, okay, all right, whatever. Okay, 4 moles of this stuff. What's carbon dioxide? What's the molar enthalpy of formation of carbon dioxide?
Just like just pay for ads.
The big chart.
Put ads on Facebook. What's my chemistry
What?
videos?
What was that?
Thumbnails.
Oh, they're the same thing all the time, aren't they? Yeah. Just me in front of the camera going like this, or like this, or like this, or something. Yeah.
Now you have 3 different options.
It just randomly picks it. I don't really care with the thumbnail.
That's why you're not.
The
at
thumbnail
1,000.
gets you the views, Walton.
You need some effort.
What's
Clickbait.
Yeah, clickbait titles.
oh,
I blew this up.
chemistry teacher destroys
Children.
conservation of mass. No, not children. Teacher eats a child. No.
You won't believe what comes next.
That's actually good, man.
No, that's terrible. No, I'm not going to contribute. I'm not going to contribute to that kind of culture.
9 out of 10 science teachers hate this.
Oh my god. Okay, what's the enthalpy of formation for water vapor? 241.8 kilojoules. Okay, it's really important that you understand that we're adding together the products but we're subtracting the total of the reactants. So how many butanes are here? 1. In mine it's 1, in yours it's 2. 1 mole of butane, and butane's like, what is it, Matt?
Negative
135.7. Negative 125.7 kilojoules per mole. Okay, and what's oxygen? 0, right? It's because it's compared to its elements. There's no difference in energy. Good. So you can figure out what that is. Yeah, you gotta go. You can figure out what that is.
Oh wait.
I'll put the key up.
So we don't write the times by 0, right? Because that would just like nullify.
But it's plus inside the big brackets.
Okay.
It's plus 0, right? And plus 0 doesn't do anything. So you can figure that out if you choose.
2657.
It was nice working with you, Walton.
No, we're not done yet.
4 minutes.
I know we're not done yet.
In
In this next example, it's asking for the molar enthalpy of formation. So you have to just rearrange. You have to make an equation and you have to rearrange it trying to find the enthalpy of formation for hexane. That's totally something they could ask you to do, right? I'm going to skip ahead and we're just really going to quickly, really quickly, we're going to talk. Hey, you know, what, Mr. Zakowski's going to walk by with a speaker, and do you know what song's going to be on?
I remember what you were saying.
I'm walking on sunshine.
I wonder why you would give a chemistry teacher.
So anyways, that's going to be because they're going to ask you. They're going to ask you what's the ultimate source of energy from this chemical reaction. The sun. Catalysts. We know about exothermic reactions and endothermic reactions, right?
Yeah.
Did you know that an exothermic reaction is just the reverse of an endothermic reaction?
Whoa, that's insane.
Whoa.
Okay, good. And then we're just going to draw a real quick diagram.
Energy.
There are 2 different activation energies here. If they one that way and one that way. If they don't specify, which one are they talking about? The forwards direction. So this is the activation energy. This is the EA forwards. And this is the EA in the reverse direction. Where's the enthalpy? How do I calculate enthalpy here? Good. It's from here. Oh, that really devolved quickly. It's here. That's the enthalpy, right? So the enthalpy is going to be negative in one direction, but it's going to be positive in another direction. And you're going to have 2 different activation energies. What's the purpose of a catalyst? What does it do?
Increases the rate of reaction and increases the rate of
Good.
reaction and provides an alternate thing.
An alternate pathway for a chemical reaction. Good. So it reduces the amount of energy required to get over the hump, and that speeds up a reaction. That's the only thing a catalyst ever does. But does it speed it up only in one direction?
No.
No, it speeds it up in both directions.
All right. Okay.